In this lesson, we are going back to our focus of the application of our quadratics, but focusing more on throughout this lesson using Desmos, and then we'll get to those equations also graphing in Desmos. But these are just some review questions, again, going back with our visual. So go ahead and pause the video and do these 4 questions on your own with these comparison of these javelin throws. And here we go. So what is the starting height of the throws? Well, notice how they were all the same. And you're counting by 2, so you should have said that the starting height was 6 feet. So right here, all 3 throws start. Now notice all 3 throws have a different landing and a certain distance in yards away from where they started. So how many yards away did throw 2 hit the ground? Well, throw 2 is here, this line in red. So if you follow it, it hits right here, 45 yards away. How much further was throw 1 than throw 2? Well, throw 1 was here at about close to just past 55, so maybe 56. So if we're comparing 45 to 56, then that means throw 1 is 11 yards further away. And what was the maximum height of the throw? 3, which is the vertex here. So the vertex was here. The maximum height that it reached was 12 feet. So again, going back to using Desmos to answer our questions here and understanding, again, visually. We're talking here about in example 1, a hot air balloon and how it's starting rising and flying away from the top of a hill. And then it shows its ascent as well and descent. So when you graph this in Desmos, so if you need to, go ahead and pause the video to graph this in Desmos. So then we can now visually see it should look, here's something like this. So this is the graph and how it should look in Desmos. So now we can answer the questions. Well, what is the starting height? Remember, the starting height is always that y-intercept, right? So it's starting here at 40 feet. How long was the ball in the air? So remember, right? This is the path of our balloon. It started at 40 and then boom. So it stays in the air for 5 seconds. At what time did the hot air balloon reach its maximum height? So at what time? So here, the maximum, our vertex, right? So that's, again, going back to our vocab. The vertex, it took 2 seconds. And what is the reasonable domain? So again, remember, right, we're talking about x values, but reasonable, because this is relating to a hot air balloon. So again, remember, right, if this is our time, can you ever travel in negative time? No. So that's why we're here starting at 0, our x value of 0 to 5. So 0 to 5, or our x values are between 0 and 5. So again, going back to that review, but we're going to continue focusing on just the use of Desmos. So again, pause the video so you can graph this model here that represents a diver. And this is how your graph should look. Remember, right, you can identify these points just like what I did by just clicking on it in Desmos. So then we can start answering these questions. When does the diver hit the water? So again, if you ever need to, trace over so you can visually see. The diver starts here, right? Because we can't be negative. So the diver starts here and then boom, hits the water, right? So when does the diver hit the water? How far out? How long? In 2.6 seconds. That's why the answer is A. What is the starting height of the diver? So where did they start? Right here, right? The y-intercept, 7.5 feet. What is the maximum height that the diver reaches? Well, it took 1 second, but what was the maximum height? 12.5 feet before the diver started going down and then hitting the water. So now go ahead and pause the video and try these 2 U tries on your own. So example 3, you're just answering one question and here's your choices. And example 4 again has these 3 questions to answer. So go ahead and pause the video and try these 2 on your own. And so now for example 3, after graphing talking about Alex throwing a rock off of a bridge, how long does it take the rock to hit the surface of the water? So how long before it hits the water? So here is the graph you should have gotten, right? Starting here and going down. So boom. How long did it take before it hit the water? 4 seconds. So that's why you should have gotten B. Then example 4. Approximately how long is the golf ball in the air? So that's the same right here, right? How long is the golf ball in the air? So going back now to this, your graph should look like this. And so again, looking at the path, right? Starting here and then boom, hitting the ground. So how long was this in the air? For 4 seconds. For 4 seconds. That's how long the golf ball was in the air before it hit the ground. What was the starting height, right? There's your y-intercept. So what was the starting height? 4 feet as well. So, or 4, so 4 feet. What is the reasonable domain? So here's our x values. Are we starting at the x value here of negative 0.5? No, because it doesn't make sense to travel a negative distance. So we're not using this section here. We're starting at 0, this x value, and ending here at this x value of 4. So we're going here from, we're going, the reasonable is 0 to 4, or x values between 0 and 4 seconds. So the reason why now we're ending with these is just going back to solving our equations. So like looking at number 5, right? We're just solving for x. Well, I notice here we have the value of 3, right? Do we have a GCF? No. So this is when we would do bottoms up and multiply. X squared minus 10x minus 24 is equal to 0. Then we can factor. The factors that we can use in this case that multiply to get us negative 24, so I need 2 different signs to add to get negative 10. Now remember, because some people would want to say 6 and 4, but the signs are different. So you'll never get negative 10 if you tried. So 6 and 4 won't work. But 12 and 2, negative 12, positive 2. But then remember, right, we're not done. The answer is not positive 12, negative 2. We now need to divide by 3. And so here we've got 3x plus 2 and x minus 4 is equal to 0. So then our solutions are x is equal to positive 4, and then use that fraction, so negative 2/3. Now, this is the solution that we would get from solving. Now you can use Desmos to graph and check. So if you were to graph and check in Desmos, if you were to graph this equation, the 3x squared here, this is how it would look. Now remember, all we need is x. So all we need are the x-intercepts. That's it, because we're solving for x. That's what we're looking for. Like if you recall, like that is like the good old, how long is this object in the air before it hits the ground, right? We're using the x-intercepts. Notice what the x-intercepts are. One of them was here at positive 4. Now, you're not going to get a fraction, but notice it's negative 0.6 repeating. So if you were to put 2 divided by 3 in your calculator, this would also match. So notice how in the end, we're just solving for the x-intercept. So here, let's do the next one. Solving, and then we'll see it by graphing. Now we do have a 2 here. What's the first step? Do we have a GCF? Yes, we can divide every term by 2 and take that GCF out. So 2 times x squared. Now 18 divided by 2 is 9x, and 36 divided by 2 is 18 is equal to 0. Now we can start our factoring. Keep the 2, right? What numbers multiply to get 18? Now notice we do have 2 positives, so our signs are going to be 2 positives. So multiply to get 18 and add to get 9. 6 and 3. So this means x is equal to -6 and -3, right? Change the signs. And if you recall, the GCF cancels out because 2 will never equal 0. So now if you were to graph this in Desmo, so if you need to, pause the video to graph, and let's see what the x-intercepts are. Notice how it matches. You get -6 and -3. So go ahead now, and if you need to, pause the video, graph this equation to see what is the x intercepts. What is x equal to? And here we go. Now, if you were to graph this as is, it is a very large parabola. You would have to zoom in quite a bit. However, all we need are the x-intercepts. So it's crossing the x-axis here at 10 and -7. And that is your 2 solution, 10 and -7.